Perfect. So the original talk was climate change, demographic transition, and subsurface and soil structure change. And one of the reason why I was looking at this is because out of the I'm not a specialist of radon at all. I rely on NIREC like absolutely for everything when it comes to radon. But one of the elements I was thinking about when I was talking to him, because he was telling me at that time that the half-life of radon is very, very short, so that the upper layers in the soil might play actually a very important role in controlling the amount of radon that escape into the atmosphere. And to give you a start, this is a photograph at Mount Kartala. It's in Africa on a volcano, and we are doing some GPR in the field with a local colleague. That's a couple of years ago. And what you can see on the forefront is like a nice bomb, volcanic bomb, that had a good idea to fall down a couple of days before we went there, hopefully not on our heads. But it was erupting at that time. So that was quite interesting. So in Japan, when you think about soil and where soil are and what are their structure, one of the elements which is, I think, of importance is the fact that it's nothing which is like absolutely fixed in time, in the sense that you have natural soils, but a lot of the soils have been actually removed, remodeled, replaced. And to give you an idea, if you go to Towada, which is in the north of Japan, there is a large city of 40,000 people there. And that city is lying on volcanic deposits. And that volcanic deposit is no good at all when it comes to agriculture. And in the 16th century, the local lord imported soil and covered the entire surface of the land with imported soil. So what you have on the map, on the soil map, and what you have actually effectively on the ground is totally different. So to give you that, that's just to give you the scale at which the soil can change. And one of the elements which is of importance today is the aging of the population, the rapid aging of population. And one of the things that you can see on the photograph underneath here is you can see actually a wall, and that wall used to be used as a retaining wall on the side of the paddy field. So the paddy field, where you have the rice which is growing in there, is filled with clay, and then you grow your rice in that. But with the depletion of the population, those rice fields became unused, and they started to use the space for forestry. But what it means that you have trees that are rooted in the soil. And if for several hundred years you had a clay cover, and the clay cover usually is quite impermeable to gas and radon exchanges, all of a sudden, when you have these vegetation changes, it means that you have like a new pathways that are created through the soil for whatever gas exchange in general, including radon, of course, will occur. And the other element that comes at play is like when you have hazards and disaster risk in those areas that are depleted, what the government does is to really remodify again all the landscape, and you have had a scrap of all the topsoil to actually have a replacement with engineered soil here. This is in Kyushu in South Japan in 2017. So you can see those very large remodeling of the landscape that I think can have effects for the local inhabitants. And to give you an idea of the scale of it and what happens notably with climate change, so that's an impact that we have been surveying in Japan post heavy rainfall that are linked to abnormal high temperature of the sea, and that's climate change. We've had this huge amount of debris flow and landslide that basically scrap the surface of the land. And when you put all of that into a GIS and you look at the amount of space that has been scrapped, in less than 24 hours, you have about 238,400 square meter of land that was totally actually modified. And that's something like 11% of the whole watershed there. And what's important to notice as well is that because we are in a country which is tectonically active, a lot of those landslides that are triggered by rainfall actually already occurring in places where you have active faults. Hold on a second, I think someone needs me to let him in, blah, blah, blah. Yeah, Peter is back. Okay. So those happen in places where sometimes you have active faults. So you have the opening of those ways up through the soil. Peter, you can hear us, I guess. I can see you back.
Yes, I'm sorry. Perfect. Yeah, I am not at a different computer now. So
I will finish.
Please go on. I'm sorry for this.
No, it's all right. Those things happen. I will finish the presentation and then let you speak.
Yes, please go.
So another example that occurred just after the example I was showing you earlier in 2017, that's in 2018 in Kobe. And we are in granite here. So of importance, I guess, for radon specialists. And again, we have the same issue. We have the topsoil that are made also of clay, so very impermeable to gas transfer, that during those events triggered by climate change, you get actually a remobilization of those soil, and then against the fractures in the rocks that are put bare to the atmosphere. I didn't put any map here, so the photograph I'm giving you here are photographed from Kobe City, and the houses that we see are Kobe City houses, and the Sabo Ente, which is the dam that we can see here, is the dam that was stopped over by one of the mass movement at that time. And in terms of density, it looks very much like what we have here on that image, where almost all the slopes that could go went during that event. So one other thing I wanted to talk about, because what we are doing with Mirek, and that's what I'm doing with you in here, is to use the ground penetrating radar that actually is just a radar that looks into the ground, and what you have on top here is what we call a shield, so that the electromagnetic signal doesn't get into the air and capture cars and trees and everything else that we don't want to see. And only underneath we have actually the antenna, which is getting the data from the ground. Yes. And this is one example of an unconformity. So just to make things very easy to understand, I went just over that tree trunk here and drag the antenna at a 90-degree angle. And those are the results. So the result that you can see in front of you, that's called a radargram, is just actually a series of traces, radar traces that are stacked together. And you have in gray the 0 in the amplitude, and then you have the positive amplitude in black and the negative amplitude in white. So that's why you have those changes in black and white. And the tree trunk that you can see, it's generated by the hyperbola here. And we get an hyperbola because the electromagnetic signal, as you all know, doesn't travel in a straight line, but it's going into a cone, at least a cone underneath the antenna. So when we get closer and closer, objects that are not right underneath the antenna, but actually a bit further away, give us this impression of having an hyperbola. And the object itself will be just at the tip of the hyperbola there. And because we know the distance on the ground, then we can calculate the depth based on the velocity of the radar, and we use actually those hyperbola slopes to calculate the velocity. And what was of interest here is to show that depending on whether you have actually hypermobility, you have presence of water or not, you can get actually different data that translate into a different velocity in the ground. And that velocity in the ground is mostly controlled by the electric permeability. And one of the difficulty that we have, so that's the relation here between C is the speed of light, V is the velocity in the ground, and this is the permeability. UR usually is set to 1, and ER is the permeability of the ground. And what we do usually is to then try to derive some properties of the soil based on those simple assumptions. And one of the difficulties is the fact that the GPR, although it's an electromagnetic method, it's only recording the electric amplitude of the signal. We don't have the the magnetic part of the signal. So when we do, and this is how it looks like, sorry. And when we do the research, so we have to combine it with what we call in geophysics inverse modeling. So we, most of the time for GPR, we use the Maxwell's equation that you are all familiar with. And we use that actually to calculate back or try to make some estimates of the other parameters in the ground. And this is an example of a model I run for a tree trunk of different diameter in the ground, and get the parameters into the equation. And I use a discretization method that have been developed by, it's written right down there, by Yi in 1996, that allows me to work in 2D space and in time. And we get these kind of results, basically, where we can see the signal that comes in and comes out, and we can modify the speed, we can modify the relative electric constants of the ground, and try to actually fit that data back into the data that we got from the GPR. So we get actually a confirmation of those properties. And then when we run the simulation in 2D, we get these kind of results showing when the electromagnetic signal gets into the tree trunk. So it can be a rock, it can be a different layer of soil, and when it's coming back, coming out on the other side, so like it wraps around. And we have then other ringing effect, because when the signal is actually moving from the side into the block, it doesn't go into one straight line, but it radiates out. So you get actually, depending on the shape of the object, you're going to have actually other ringing effect that you can use. And one of the work that I'm doing right now is to work on the shape relation to actually the position and the slope of the different elements. And in the ground, that's what I was adding earlier. When we go in the field, here we are looking at paddy field in Kumamoto Prefecture, and we had an earthquake with a different, quite a strong earthquake actually in 2016 that created those different lines that you can see on the ground, those different ruptures. For some reason, I cannot see my mouse, that's why I'm running. Okay, yeah. Those different ruptures on the ground. And one of the questions we were having is like, what is the structure inside? How deep are they? And also, well, what are their orientation? For us here, it's maybe not of so much importance. The importance at that time was to define whether those cracks could actually trigger slides later on. But back to what you guys are doing and what we're doing together. One of the questions we can ask is like, despite of having 1, 2, 3, 4 different groundbreaking lines on the floor here, on the ground here, we can also ask, is there anything that we can't see because the breakage didn't reach the surface? And how many soil layer those line breaks? And what we get are those kind of radarograms, same kind that we got earlier. This one is a bit longer, that's why it looks a bit different. And you can see actually the change in the dielectric properties that are linked to the soil grain size. So you can see when you have a lot of blocks and rocks, like you have those small hyperbolas, that shows actually that you have a lot of blocks, or that for what Mirek was showing earlier, it means that the ground is very permeable. And when you have things that are more like what we have on the side here, you see at the top, where the lines are a bit more regular and you don't see actually those small variations, it means that all the elements that constitute the soil are in a size which is inferior to the resolution of the antenna to detect individual objects. So we can have an idea of actually what is the size of the object that are in that soil. And we use that to create this kind of graph that you can see underneath, where we can have the different soil layers, We can see the underneath here, this is the bedrock. And you can see also the fractures that go across the bedrock and in the soil. And if you look at it, you can see very clearly here. You can see all those breakage and this breaking line. Usually you won't get that into a cultivated soil because it's going to be quite linear. And we can infer without much doubt that those breakage are actually created by the earthquake. And another thing that we do, that's the rules, that's the signal itself. But then you can work on the envelope of the signal. You can use work on the phase. That's a combination here where I work on the phase and the envelope of the phase. And I look at how it changes through the soil. And we can see in those graphic, actually the similar patterns where we can see when we have a breakage actually through the soil, because you have those different elements that are creating those modification in the structure, and the modification in the structure in turn modify the phase of the signal. That was, I wanted to talk to you guys about the GPR, but when I was listening to Mirek, I just added that slide as well. So it's in Japanese, so sorry for that, because it comes out, it's going to come out in a different publication, in a Japanese journal. But here, shashin means a photograph. So I take a series of photographs actually of the soil here, like the ground, and I dig a hole in it, then take a photograph afterwards again, and I get the 3D model, which is a point cloud. And that point cloud has a resolution which is inferior to 2 millimeters. The error I get on the surface are like 1 to 2 millimeters when I've done my job properly. And what I do is that I take a series of photographs of that to create that model before I dig the hole, then take the photograph again. And by weighing the mass of the sediment and using what we call a DOD, which is a difference of DM, or DM of difference, sorry, meaning that we compare the two surfaces to get a volume of that hole, then we can actually have a clear idea of the density of that soil. So Mirek was talking about showing that scale actually of porosity, which is an ideal scale, but we can now actually improve that scale and look at actually how closely packed the grain are. So I didn't invent the wheel here. There are many different methods that are used to measure soil density, but there were none so far that were available for coarse grain, mixed grain, and consolidated sediments. So it means a lot of different formation. So using that, we can have a better idea actually of the real density of the soil and not just an estimate based on the grain size. And on the right here, you have this map, which is Hodaka in the mountain in Japan. And we have this debris flow fan. So imagine you have a debris flow that went down and the debris flow stopped, pushed what they call ryuboku here, which is like drifted wood. And you have this mass of sediment that's up there. And those are 8, 7, 9, and those different points here are places where I took sample and did those measures of density. And we have exactly the same material. We have the same kind of grain size, except a 1 or 2 sample. But we have a huge variation in the density. And when I say huge, it's between 1.6, 1.7 to something like 2.1, 2.2. So it's a lot of change. It means that we then in turn have a very different pore size, and then linked to that pore size, a very different gas transfer potential within the soil. So I thought I would show that to you guys because it's pretty new, it's not published yet. That kind of research has not been done yet, but I think it has some quite interesting potential to refine some of the equations that you guys are using already. And that was my talk. So I tried to make it very, very quick so that we gain some of the time and give some more time to those who want to speak a bit longer. But basically in Japan, in Taiwan, climate change induced soil modification are huge. This is happening, and it's happening very often where we already either have active volcanoes or in the vicinities of active faults. And on top of that, those mass movements means that we have actually modification of the soil in different locations. So when we think about our soil map, maybe we should think about something that can be actually reactualized depending on the different events that we have. And blah, 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 blah. And I think that GPR has quite, can provide some opportunity to better image the soil structure and try to link that soil structure down to the potential for radon transfer into the soil.